Hey everyone, so today I would like to point out that, as students, parents and teachers and many other people always explain to you the importance of math. Whether it's for a career or doing something like taxes, they always seem to skip out why you should like math as opposed to why you should just know it. So that's what I'm going to try to do today with fractions, proportions, and graphical representations. So as you can see, artists all use math in their compositions, so whether it's a guitarist, a pianist, or even a DJ using their software, they all have to use math, particularly fractions, in their compositions. So we're going to look at first is the notation that is used for musicians. So looking at that, we have representations as parts of a whole. So a whole in music is this entire bar right here we call a measure. So what a measure is how the artist splits up their song into smaller segments. So we can see here that the first note, the whole note, represented below it by pieces of a pie, is the entire thing. So if you were to hear this on a guitar, it would sound like this. So that's the entire measure, all 4 beats, which is what measures are usually divided into, but we'll get into that more later. So looking at the second, the half note, we can see that obviously it's half of the whole note, as represented by the pieces of the pie. So as opposed to the whole note, which goes through the entire measure, we'd have 2 half notes, which would sound like this. And that plays out, and that's the end of your measure. So then half of the half note then is the quarter note. Now a quarter note is sometimes more common, sometimes not, depending on the piece, but looking at the pieces of the pie, that is 1/4 of the measure. So just like the half note, when played, to take up an entire measure is 2 of them, the quarter note, which is half of that, is played 4 times in one measure. So, as represented by the guitar. So that's the basic notation in a nutshell. So we're looking at parts of a whole, whereas the whole in what you're used to could be pieces of a pie. In music, it'd be pieces of the measure. Now moving on to something that the notation is actually used in, we get to the notion of a time signature. Now what the time signature is a way for the artist to sort of arrange their piece according to the sound that they want. So what we look at first is this number right here, which is 4/4, which is the time signature of this measure right here. So what we look at first is the bottom note, or the bottom number. So what that means is the 4 represents 1 beat, so you'd be looking at a quarter note. So to put this in more math terms, you'd have 4 times your quarter note makes up one of your measures. So then looking at the other time signatures, we'd see that 3/4 would be divided into 3 per your quarter notes. So we'd have 1, 2, 3 quarter notes. Obviously quarter notes don't look like that, but I'm not the best artist. And then looking at this, 6/8 is a little bit different because in math you'd usually reduce a fraction. In this case, for 6/8, this would be usually 2 measures with 3 each, and they're punctuated a little bit differently than 3/4 would be. Now the easiest way to hear this is to use some examples. So the first song I picked was The Strokes, Last Night, which is an example of 4/4 time. As you can see there, they have 4 quarter notes per measure. Now the second one I'd like to look at is Beck's Sing It Again, which is a good example of 3/4 time.
Let's go.
Which is easily heard in those beginning notes. Now for 6/8 times, the most iconic one is the Beatles' Norwegian Wood. So the Beatles' Norwegian Wood sounds like this for 6/8 time.
I once had a girl, or should I say, she once had me.
So you can see there that the 3/4 and the 6/8 have the same beats per measure, as they should mathematically, as they're both represented as, 3/4 is half of 6/8, as you would reduce it to. But aside from these common time signatures, there's many others. So if you're looking at grime, for example, it's a genre that usually uses 2/4 time, same as something like polka. But when you start getting into more metal or jazz, you could be looking at 5/4 time, which is pretty common, 12/8 time, stuff like that. So you'd be looking at a whole bunch of different fractional representations of how you're dividing the one whole measure. Now what we usually look to next, in mathematical terms, would be sound as a wave. So as you can see here, the guitar strings, when you pluck them, because they're fixed on both sides, represents a moving wave. See that right there? So in math, that looks like a sine wave. But when we look towards something like a woodwind instrument or a brass instrument, as represented down here, we have a tuba of air. So that still works the same way as in waves, and you could mathematically represent it as one, but it's not quite the same thing. So if I were to graph one of these waves over here on my graph, you could see that one full wavelength could be represented like that. Now in music, we look at frequency of sounds often. So we usually measure that in hertz, which is just a term for 1 cycle per second. Now something that's interesting that happens with this is if we look and we have the wavelength, so go through here to there, obviously not the best pictorial representation, but you see what I'm getting at? If we have the wavelength, what we do is we increase the pitch and go up 1 octave. So what an octave is, in music terms, is just the interval between one pitch and another that has double or half the frequency. So we get back to the concept of fractions here. So if we have, say, a middle C, which has a frequency of 262 hertz, and we want to go 1 octave, which is the next in the pitch scale above it, so it would have a higher sound, we would turn that into 524 hertz, which is just 2 times this, right? But if we want to go 1 octave lower than that, we can go from our 262 and we would cut that in half to get 131. So the 131 hertz is 1 octave below the 262, which is the middle C that we started with. So basically what we're doing is doubling or halving the frequency each time as we want to go up or down 1 octave. Now the reason that octaves are important in music is scales. So if we're looking at what we have here, this is the C major scale. Now the C major scale is one that you'd encounter most often when looking at music. So that'd be right here. And what we see here is that we have a C here and a C at the end. So between those two frequencies, we have 1 octave, which we just talked about. So each note on this scale would be twice the one before it, or half the one next. So to go from here to here, we would double the frequency. Again, we would double would be the entire thing, sorry. So each of these would be some fraction of that. So to get from the C that we have at the end, the first C, to the last C, this is twice the frequency, so 2 times that. Now a particularly important scale that was used in ancient times by somebody you might have heard of, Pythagoras. So if you're a student, you probably have heard of the Pythagorean theorem. So Pythagoras' scale was a frequency ratio that had all intervals based on the ratio of 3 halves. So if we had, say, 100 hertz to start with, the next octave up would be that times 3 halves, giving you a frequency of 150 hertz, right? And that's how you would begin building your scale. So instead of C major, maybe you could build something else out of that. So I hope you guys have seen that through all of this, math is a very integral part in music. It's shown not only in the physical strings of a guitar or the pockets of air in such as a brass instrument, but you can see it in the visual representations that musicians use to record their music. It's used in the time signatures, and if you guys want to look a little bit further into this, you can see all of the different geometric structures that you can build out of music theory. So I hope you guys can see that math is a little bit more interesting than you guys thought before. So thank you for taking the time to watch this, and I'll see you next time.